Okay, good morning. I'd like to start by thanking the very generous award from the Adelis Foundation and for this honor. And I'd also like to thank all of you for being here in this hard time. It's really heartwarming for us to see so many guests from abroad. So I'm going to tell you a little bit about what we do. Now, just as a ways of background, we all use electricity every day, of course. In fact, we use more than we need to because some of the electric energy gets lost on the way. And we all know this. We know this by looking at our electrical bill. And we know this when we use our laptop. We feel the dissipated heat on our knees. Now, imagine what we can do if we could use electricity without any loss of energy. If really no energy would be lost on the way. For example, some of you may have heard about these super fast trains that were built in Japan that reduce the friction by levitating over the tracks. Now, how is that possible? That's possible because they use a superconducting electromagnet using a material which has this property called superconductivity, which means that this material can sustain an electrical current with no loss of energy whatsoever. And to understand how such superconductors work, we have to dive a little bit into the quantum mechanics that governs the behavior of electrons in materials. So what actually happens when a metal conducts electricity is that electrons flow individually one by one and carry the electrical current. And as they do so, they actually bounce off the atoms or the ions making up the metal, and thereby some of their energy that they carry gets lost, gets dissipated. Now, when a material becomes superconducting, what happens is that the electrons, rather than moving individually, they bind into pairs, and these pairs can move coherently through the material without bouncing off the ions at all. So this is a quantum mechanical coherent phenomenon, and this is of course wonderful. That means that this material can carry an electrical current so large that it would melt a non-superconducting normal metal wire because so much of the energy would be transformed into heat. However, there's only one challenge, which is that it turns out that materials only become superconducting at extraordinarily low temperature. Now, this is not something you can reach in your kitchen freezer. We're talking about the first materials that were discovered to become superconducting, only become superconducting at the temperature of around 270 degrees centigrade below zero. So this is extremely low temperature, and of course, just cooling materials to such low temperatures by itself takes a lot of energy, and that limits severely the applications of such materials. Now, since their first discovery, much better superconductors were discovered that superconduct already at a relatively high temperature of around 180 degrees below zero centigrade. Okay, this is actually so cold that air becomes liquid. Here's a little video that demonstrates how superconductors behave. So in the bottom here, there's a dark disk. That's a piece of superconducting material. And this is immersed in liquid air that cools it down to such low temperatures that the material actually becomes a superconductor. And the shiny cube is just a piece of magnet, like a fridge magnet. Okay, and what happens is that the magnet creates a magnetic field. That magnetic field induces an electrical current in the disk, in the superconducting disk. That electrical current can flow indefinitely because it's a superconductor. It can flow without dissipating any energy. And in turn, that current by itself creates a magnetic field that repels the magnet and causes it to levitate. This is actually how these levitating trains actually work. So this is called superconducting levitation. Okay, and this is really a tabletop experiment you can do. Okay, so I'm a theoretical physicist, and my longer-term dream is to be able to come to my friends in the lab and tell them, try this and that compound in your lab, And that would be a room temperature superconductor. Clearly, if we had a material that would superconduct already at room temperature, that would transform our world. Okay, so how do we do that? How do we predict new superconductors, and how do we understand the mechanisms and properties of superconductors? In principle, easy. Okay, so we know exactly the quantum mechanical laws of nature that govern the behavior of electrons and atoms in a material. It's all encoded in this simple looking equation. All we need to do is just solve that equation, and voila, we can predict the behavior of any piece of material that we want. So we can predict new superconductors and new materials. Again, there's only one little problem. It turns out that this equation turns out to be so complex that we can only actually solve it for 1 or 2 electrons. Anything more than that would require huge computers. Okay, so we need to do these computations on enormous supercomputers. And in fact, in order to really predict from first principles a new superconductor, even all the world's biggest supercomputers combined would not be enough. So this is an enormously challenging task. So it looks like the mathematical complexity of quantum mechanics is like a mighty fortress that hides the secrets of superconductivities from our eyes. Okay, and what we've realized in the last decade or so in my group is that one doesn't always have to break into the fortress through the front door. Sometimes there's a little mathematical trick. Okay, and don't worry, I won't explain the trick, but sometimes there's a little trick that allows us to just bypass the wall and take a peek inside that can reveal to us some of the secrets of superconductivity. Okay, and I'd just like to show you a little example that we've worked on in recent years. Okay, and this is a phenomenon called the quantum critical metal. So, for instance, there's this compound over here. So it's a material which is made out of a combination of these different elements: barium, iron, arsenic, and phosphorus. And it turns out that this material, under different conditions, can display vastly different behaviors. So under some conditions, this is an ordinary metal. Under other conditions, this is what's called a magnetic metal. So it turns out that in an ordinary metal, every electron is like a little magnet. It has a property called spin. And in normal metal, these little magnets wiggle around such that on average, their orientation cancels. In a magnetic metal, these little magnets freeze and point in a certain direction. Now, right in between these two states or phases of matter, there's sort of a sweet spot, which is called the quantum critical metal. And it turns out that right there, the material tends to become a high-temperature superconductor. Okay, and what we've been able to do over the past few years in my group is to apply our mathematical trick to actually simulate this behavior on a computer. Okay, and here's a so-called phase diagram. This is like a map showing how the material behaves under different conditions, in this case, composition and temperature. And here on the left is the magnetic metal, on the right is the ordinary metal, and right in between there's the sweet spot, the quantum critical metal, where the material becomes a superconductor. This is a phase diagram taken from actual experiments, and here's our computer simulation actually capturing the same behavior. Okay, and we hope, looking forward, that our new technique can give us insights into the mechanism and the inner workings of superconductivity to understand this phenomenon and hopefully find new materials that can answer our energy needs. Thank you very much.